Now, we have alluded to this before, but let's be very explicit here. Biochemical pathways are a series of enzymatic reactions in which initial substrates are converted to intermediate substrates by enzymes in the pathway, such that finally there is an end product. And often these enzymes, as we mentioned, are in multi-enzyme complexes. Not always, but often they are. And because a biochemical pathway starts with initial substrate and an end product, and there are intermediates along the way, considerable energy can go into the breaking down of these substances. And for that reason, it's often a system of feedback inhibition has evolved in biochemical pathways. So that here's our biochemical pathway on our left here. We have 3 enzymes. We have an initial substrate and 2 intermediate substrates before arriving at the end product. Well, if there's plenty of end product around in the cell, it would behoove the cell to have a system whereby the biochemical pathway could be shut off. And that is achieved by feedback inhibition. When the end product is at high concentration, it will bind to an allosteric site. So at low concentrations, the allosteric site won't be bound because there's not many molecules of the end product around, and the pathway will proceed to produce end product. But if there's plenty of end product around, an end product can bind to an allosteric site on one of the enzymes of the pathway, let's say enzyme 1 here, and that will block non-competitively, that will inhibit enzymes so that the initial substrate is not converted to an intermediate substrate, and the pathway is therefore blocked, which energetically makes exquisite sense for the cell. Now, what I'd like to turn to briefly here is the theoretical evolution of biochemical pathways, because they can seem very complex to us. Let's imagine a primitive organic soup that existed in the environment, let's say, and that organic soup had compounds in it, A, B, C, D, E, F, G. And really, we're going to say that substance A here is utilized by cells in this primitive environment early in evolution to perform certain functions. So the cells need compound A, molecule A. Well, that's great because there's plenty of it around in the organic soup that exists, and cells that are living there are happy using compound A. But what happens when compound A becomes depleted? Well, that can be a real problem because now the cells need A, but where are they going to get A? Well, cells that would evolve a mechanism, for example, to say convert a high energy compound B to A through an enzyme, call this enzyme 1. Well, then cells that could utilize an enzyme, an evolved enzyme that would convert high energy compound B to A, B providing the energy for this catalysis, that's great. We have an enzyme, and that's wonderful. But what happens when B gets depleted in the environment? Well, then selection would favor the evolution of an enzyme, let's say enzyme 2, that can convert, say, substance C to B, let's imagine. And finally, we can proceed down this line here so that eventually we end up with something that looks like this. Let's partition this off here. We now have a biochemical pathway that goes G, F, E, D, C, E. Each of these steps, enzyme 3, enzyme 4, being catalyzed by enzymes, such that we have a complex biochemical pathway that has evolved, but it's evolved in a way backwards. The later steps in the pathway are the ones to evolve first, and the earlier steps in the pathway are the ones to evolve later as substances became sequentially depleted, high energy substances became sequentially depleted in the environment. So that's a hypothetical scheme of how a biochemical pathway could have evolved early in life's evolution. And with that, we'll finish off general considerations of biochemical pathways now, and we'll move into specific biochemical pathways that are involved in catabolism and anabolism.